In this video, we're going to look at intermolecular forces. Intermolecular forces, a couple things. Number one, they're not actual bonds, like a covalent bond or ionic bond. They're simply the attraction between adjacent molecules. So imagine you have two water molecules next to each other. There are ways that they can either be attracted by each other or repelled by each other. So it's an influence. And again, if it's an influence and not an actual bond, it's going to be weaker than any of the bonds. The first intermolecular force we're going to look at is what's called molecular polarity or dipole-dipole forces. Real simple concept here. If you've got a molecule, one side of the structure has more electrons around it than the other. So we have hydrochloric acid. Look here, there's more electrons around the chlorine than there are in the hydrogen. So if there's more electrons on this side than the other side, it has a dipole. Now there are a couple ways that we can do this. One way is the book will show that you draw a line with an arrow, and where the arrow starts is a plus side, so that side we treat as slightly more positive, and the other side of the bond is slightly negative. Another thing that is often used is the delta symbol. What you will see, again, somewhere adjacent to the structure, you will see this symbol, and what it's going to say is one side of the symbol or structure is positive, the other side is partially negative. So this symbol simply means partially. If we look at an example of a water molecule, and again we're looking at each bond. First of all, we remember that this is a bent structure. So if we draw lines along the bond path, we would say the electrons are concentrated towards the oxygen. Electrons concentrated towards the oxygen. Therefore, what we have is this side of the structure compared to the oxygen side. So the hydrogen side compared to the oxygen side is more positive. So we have two things here. We are looking at the bond polarity, but then also the overall molecular polarity. So if we look here, this does have a greater concentration of molecules near the top, or electrons near the top, not near the bottom. Now, the other thing I want to show you is a couple other molecules. Well, we've got the ammonia molecule. So here we can see the ammonia molecule, that there's a greater attraction of electrons towards the nitrogen. Therefore, the nitrogen side is partially negative, and each hydrogen is partially positive. Now, what's interesting is we look at something like carbon dioxide. Carbon dioxide looks like it's polar. The carbon is partially positive. The oxygens are partially negative. But here's the difference. If we look at this structure is symmetrical. One side of the structure is not any different than the other side. We can cut it in half in either direction. Well, the top is the same, the bottom is the same, the left is the same, the right is the same. This is different. So what we have here in the example of carbon dioxide, there are polar bonds, but it is a non-polar molecule because of symmetry. Now if we look here, that's not the same case, because if we know the structure of an ammonia molecule is a triangular pyramid. We go back to a water molecule, it's not linear, it's bent. Why is that different with carbon dioxide? Because it is a linear molecule. So look at carbon tetrachloride, CCl4. Again, we've obviously got four very distinct polar bonds. but all four of them are symmetrical. This is a tetrahedral. So if they're all four symmetrical, this is a non-polar molecule. So that's the thing you've got to understand here. There can be polar bonds, but that does not necessarily mean it is a polar structure. So here's some things just to think about as we talk about polarity and dipoles. Right? First of all, molecules can have several polar bonds. That is definitely possible. The question is, can the individual polar bonds add up to make it a polar molecule? Okay? So what is the one things we're looking at? We're looking at symmetry, and we're looking at the shape of the molecule. So if the polar bonds cause the molecule not to be balanced or equal, then it's a polar molecule. If the polar bonds cancel each other out, then the molecule's nonpolar. Hence, there's probably something in the symmetry or the shape. Things to remember here. If a polar structure has to have polar bonds. Another way, a nonpolar structure could have polar bonds, and more likely does have polar bonds. Now, one of the interesting things we'll look at here is I'll pause this and I'll set something up, and I'll show you here in a second. Alright, what I want to show you is a simulation I have set up. We're going to be using more and more of these as we get into different things. So in your blackboard here in section 5, there's a simulation here that's called molecular polarity, okay, by the PhET simulation. So what I'm going to have you do is actually click on this, and we're going to run it. It is Java based, so you can see here you're following through what I'm doing. You're going to open it. And it's pretty neat here. You can see some things here. First of all, let's imagine there's just two atoms here. I can say, all right, this one's going to be the more electronegative atom, and this one is the less electronegative atom. So what do we see here happen? There's a greater attraction of electrons to the atom A than atom B, more electronegative. Let's look at electrostatic potential. So which side is more negative than the other? A is more negative, more red. B is more blue. Okay. Right. Now, let's say we do something here. Let's put the partial charges on also. Let's say element B is now more electronegative, element A is less electronegative. Not only do we see it, the arrow pointing to the right, we also see the delta symbol. And again, we see more negative red, more positive blue. Say we look at three atoms. What if all three atoms are identical? Then there's no dipole. Well, what if all of a sudden we say C is more? Well, there we see not only is there a bond dipole, but there's also a molecular dipole. Let's say we make A more negative, electronegative. Again, we see there are two bonds that are dipoles, and it's creating a molecule or molecular dipole away from B. Let's just switch this around here. It's almost like vectors in physics. So again, we see here elements A and C are very low electronegativity, partially positive. B is more electronegative. So we see two bond polarities, bond dipoles forming towards B, and an overall molecule polarity or molecular polarity. You can also jump to the real molecule here and kind of play around and look at some things here. So it's interesting here that you can see what's going on with those. So definitely something I want you to kind of look at. All right, the next type of intermolecular forces is called hydrogen bonding. This one's real simple to understand. If a molecule has hydrogen in it, it could have hydrogen bonding. Here's what we're looking for when we talk about hydrogen bonding. In hydrogen bonding, we're going to have a hydrogen that is going to be attracted to lone pairs of electrons on other molecules. So what we have here is a hydrogen. It's going to be attracted to that lone pair of electrons. Hydrogen attracted to lone pair. Hydrogen attracted to lone pair. and so on and so forth. And we can just imagine this continues on and on and on and on until there are no other pairs. Now, what does this basically do? Well, this does create a stronger attraction force. It does cause bond energies, or not bond energies, but boiling points, melting points to go up, increases density. This is one of the reasons in water it's solid floats in its liquid, or floats in its liquid because it's less dense. Whole kind of things that we'll talk later in the year. But this does create a stronger attraction between the molecules, therefore does change some of its properties. Another one we're going to look at is ammonia. We notice here with ammonia, it's the same concept. You have certain certain hydrogens attracted to lone pairs of electrons on the nitrogens. The difference is here, there's not as many there's not as many lone pairs of electrons. So there's hydrogens that are not necessarily going to be able to pair up or be influenced by a set of electrons. Whereas if we look back here at water, there's a lot more interactions. You have on an oxygen atom, you have two pairs of electrons that can be influenced by, or a hydrogen atom could be influenced by them. We go to ammonia, you have one pair of electrons. So just the opportunity for a greater amount of influence to occur decreases as we look at ammonia and other substances. All right, the last one then, it's called London dispersion forces. This is the weakest of all of the forces. It does occur in all atoms, so that's kind of good that it's something that we don't have to remember certain elements. But it is temporary in the different atoms and molecules that it occurs. So why is this temporary? Well, first of all, electrons are always constantly moving. They are never stopping. So because they're never stopping, this force could show up and then it could disappear. It show up, disappear. So what happens? Because they're constantly moving, there could be an opportunity where there's an unequal distribution of electrons. And if there's an unequal distribution, then it creates a dipole. But it's going to be a temporary dipole. All right, simple example here. Say we've got element A attached to some molecule, and here's another element B attached to some molecule. Let's just say electrons are floating all over the place, and in a given instant, there is an electron imbalance, such as something like this. So what we've just created is this side of the molecule is partially negative, this side's partially positive, this side's partially positive, this side's partially negative. So what do we have here? We have a partially negative side near a partially positive side. So guess what happens? Opposites attract. Those two molecules are influenced by each other. Now, that's instantaneous because in the very next second, if these are the electrons, they're balanced and there's no attraction. Well, now let's say we do something else here. Let's say now all of a sudden that there is a greater distribution of electrons on this side and less on the right side of that atom A. And then all of a sudden, atom B, the distribution changes again. So it's almost the opposite effect of that first situation. Well, now what do we have down here? We have a partially positive side to the atom, partially negative, partially negative, partially positive. Opposites attract. So there's an intermolecular force creating a sense of attraction, therefore creating slight property changes. Well, now let's say those have all been attraction. Well, let's say something happens where there's a big concentrations of electrons on this right-hand side of atom A and not very many on the left. Let's say the same thing happens to the left side of atom B and not very many on the left. So we have here a slightly negative molecule, or slightly partially negative side, another partially negative side, partially positive, partially positive. So the two partially negative sides are near each other. So guess what? they repel. So you can see here this could cycle back and forth. Let's just one more time. Well, maybe now this side becomes the positive. This side becomes negative. This side becomes positive, or more positive. This side becomes the negative. So we've got a partially positive here. Oops. A partially positive. And again, they repel. Very next instance, maybe they come right back here to the point at which there's no attraction. And then they go back to they are attracted. And they cycle back and forth through all these different possibilities. So you can imagine these are all, it's changing back and forth between them. So it's a temporary force, temporary attraction, temporary repulsion, nothing. And it goes back and forth. So again, this is why it's the weakest, because it's not a continuous occurring positive attraction between two different molecules. So again, small sampling of another way that molecules are influenced by each other does slightly affect their properties and characteristics, not as dramatically as actual bonds, but again, it is definitely something that influences and changes some of those properties and characteristics. Okay, so that's it for that.